Welcome to the course of Two-Dimensional Signal Processing Principles and Practices. I'm your teaching assistant. So in week 3, we have seen one-dimensional discrete Fourier transform, two-dimensional discrete Fourier transform, linear convolution, circular convolution, and fast Fourier transform, overlap method, oversave method, and row column wise implementation of two-dimensional discrete Fourier transform. In this lab session, we'll implement these concepts one by one in MATLAB. Now, since we have opened MATLAB, so we can click here, open MATLAB online. Now, we are here. You can see the folder which we are in right now and the files which are in the current folder. And then there is this workspace and we have command window. Okay, so now first we need to open a new script. So you'll go here and create a script. We'll write all our code here in the script. Okay, so I've already created few scripts for the ease of this session. So let's open that. So first let's understand linear and circular convolution. CLC clears everything in the command window, and clear all, it clears everything that's stored in the memory, and the close all closes figures and all the windows that are open. So here let's represent our input signal and our impulse response of our system h of n. So like we have mentioned here x of n, which are basically the timestamp. We have mentioned it like 0, 1, 2, 3, 4, 5, and the value corresponding to each time step we have mentioned it here, which is 2. So basically the x of n is constant input sequence of value 2. So similarly, like we have h of n here, again like we have taken the time steps of h of n, then we take the value of this signal, impulse response of this h of n, which is 5, 4, 3, 2, 1. These are basically the amplitude values corresponding to x equal to 0, x equal to 1, x equal to 2, x equal to 3, x equal to 4, and x equal to 5. Since we know the total length in linear convolution, it's like the L plus M minus 1, basically the maximum length. So here length of x plus length of h minus 1. So we mention here x equal to x, and then we create this sequence with the zeros. Similarly for h, we create the output variable that we define as zeros of 1 comma maximum length, which we have mentioned here. So after that, so we basically what we are doing here is we are doing the linear convolution here. So we write it for I equal to 1 to maximum length, for j equal to 1 to I, yi, like each output instance, yi equal to yi plus xj into h of I minus j plus 1, and then we'll display the output y and draw the figure of it. But since this is a discrete time sequence, so we'll draw the plot. And now let's run this code. Okay, we can see here value of y, we have got the y equal to 10, 18, 24, 28, 30, 30, 20, and similarly the corresponding values you can check here. So since the total length of the sequence x was 6 and the length of the sequence of h was 6 as well, so the maximum length will be x plus h, length of x plus length of h minus 1, which will be up to 11. Okay, so now this was a traditional way of doing the linear convolution. Now let's do linear convolution using the MATLAB built-in function. Basically the MATLAB provides some built-in function for doing the linear convolution. Okay, so let's try to use the MATLAB implementation of this linear convolution. So for this, like we will we have our code here. So again we will mention x of n and h of n. Okay, or we can we have already mentioned it here, x of n and h of n. So we will write y1 equal to convolution con of x comma h, and let's try to check the result. So we can see both these functions, both these results y and y1 are same, except that here we have we can see there is a zero padding. Okay, so this zero padding can be eliminated if we take these values. If we mention these again, I think now it should not give us the zero padding. Correct. So we need to mention the timestamps here as well to get rid of this zero padding. And we have replaced all this code with the simple built-in function provided by the MATLAB, which is conv. So now let's try to do linear convolution in frequency domain. Now we have to mention the maximum length, which is already mentioned above as well. So maximum length is length of x plus length of h minus 1. Okay, so this portion is same till now. Okay, in fact till here the portion would be same. Then we'll save x as x comma zeros 1 comma length of h minus 1 and h equal to array of h comma zeros 1 comma maximum length minus length of hn. So now we'll perform our FFT, which is basically the Fourier transform function provided by the MATLAB. So this gives us Fourier transform of x. Similarly, in order to get the Fourier transform of h, we'll do FFT of h, and we store these variables as XFF and HFF. So now we know that once we have converted our signal input sequence from time domain to frequency domain, like we can do the multiplication and then we can do the inverse transform to get the linear convolution. So first let's do the element wise multiplication of these signal in the frequency domain, which is YFF equal to XFF, and element wise multiplication, which is represented by this with the HFF. Okay, so then we'll do the inverse here. We'll do the inverse Fourier transform in order to get back signal in the time domain. Okay, so we'll do inverse transform of this YFF and it gives us YIFFT, which is basically the signal equivalent to Y or Y1. So we'll check. Now define the timestamps 0 to length of x minus 1 and we'll try to plot this signal. So since it's a discrete time signal, we'll use the stem n comma YIFT. So let's try to see if it gives us the same result. So we can see that the values are same. So the values obtained by doing the linear convolution in time domain and the element wise multiplication in frequency domain are same. Now let's see the circular convolution. Okay, if we'll just comment this section. Okay, now let's check the circular convolution. Okay, we have taken the same input sequence here. Okay, so same input sequence has been taken, which is x and h. So the built-in function provided by MATLAB for circular convolution is ccon. Okay, so here ccon. So when we use this function on x and h, okay, so one more argument we have to provide here is maximum length of h of n, x of n. Okay, so when we perform this operation, it will give us the circular convolution, which is here. Okay, it has done this code as well. So basically we'll try to understand this code now. Let's do the circular convolution using the Fourier transform. Okay, so first we will define the maximum length, okay, which is n circ maximum length of hn comma length of xn. Then we'll perform the FFT on x and FFT on h, which is the, like here we have performed FFT on x, FFT on h, and then we'll do the element wise multiplication, because like we know if we change the time domain to the frequency domain using the Fourier transform, there's this property that the circular convolution in time domain is equal to the multiplication of these input sequences in the frequency domain. So that's why let's do the element wise multiplication in frequency domain, and then in order to get back the convolved signal, we have to do the inverse transform. Okay, so here we do the inverse transform from frequency domain to the time domain, and we save this as the fy underscore FFT circ. So now we'll check if these two results are same. We can see here in the command window. So the results obtained by performing here the circular convolution function. We have another case for performing the circular convolution and linear convolution on a 2D signal now. So earlier we were doing the 1D signal. Now let's perform linear and circular convolution on 2D signal. Okay, so now we have two input sequences, fn1 comma n2, which we have saved as variable f2, and then we have another input sequence g n1 n2, which is saved by the variable g2. Okay, so these are given here. So now first let's try to perform the linear convolution, okay, on 2D signal, which we can do simply by, like, in case of the 1D linear convolution, so the MATLAB built-in function which was used was the conv simply. Now in 2D, in case of 2D, the MATLAB built-in function for performing the linear convolution is the conv2. Linear convolution of 2D signal will be like conv2 f2 comma g2. So we'll try to display, two-dimensional linear convolution and display y2 linear, which is their linear convolution. Okay, so let's try to check our answer. Now we have run this code and the two-dimensional linear convolution is obtained here, okay, as we can see here. So now let's move to the circular convolution depending upon the periodicity of the signal. So periodicity of 2, so we'll write n1 small equal to 2, n2 small equal to 2 here, and we'll try to do the Fourier transform of a 2D signal, which will be done by FFT2 on f2. Okay, this is the signal, so we'll do the Fourier transform on this signal, and we'll mention our periodicity n1 small and n2 small, which is 2, periodicity of 2. Okay, similarly for the case of g, we'll save it with the variable g small, and we'll perform the FFT2 on g2 with the periodicity 2, n1 small and n2 small. Okay, now let's try to, okay, now let's try to check the results. Okay, so okay, here we can see the linear convolution, although it was 3 cross 3 matrix, the circular convolution in this case is a 2 cross 2 matrix. Now let's try to take the case with the periodicity 3. Okay, so here we'll write n1 required, n2 required. So we'll take n1 required equal to size of f2 comma 1 plus size of g2 comma 1 minus 1, which is basically 2 plus 2 equal to 4 minus 1 is equal to 3. Similarly for n2 required, it will give us the 3. Now here we have done the zero padding. Okay, so now like let's try to find the Fourier transform of this. So we write f padded, this is the padding on the function input sequence f, and g padded is padding on input sequence g. So FFT2, now we have performed FFT2 on f2, but in this case the periodicity is 3. Okay, n1 required, n2 required. Similarly in case of g padded, we perform FFT2 where the periodicity is 3. Okay, so now the circular convolution is in this signal is exactly similar to the linear convolution of a 2D input sequence. So we can see there's no wrapping happening here in this case. Okay, so now let's move to the next topic, which is the DCT. So we'll do the similar things. We'll clear the command window, we'll clear all the memory which the workspace has taken, and we'll close all the windows. Now in case of DCT, let's first start with the 2D DCT of a 2 cross 2 input sequence, which is given here, x equal to 1 2 3 4. Okay, so let's try to check the input matrix x should give us the same matrix. Okay, okay, as you can see here, so our input sequence x is 1 2 3 4. In case of DCT, we have the MATLAB built-in function, which is DCT2, which performs 2D DCT on the input sequence x and gives us the DCT coefficients. Okay, so then C here are the DCT coefficients. So let's try to check the DCT coefficients here. Okay, so the two-dimensional DCT coefficients for our input sequence x is here. Seen here, as you can see, two-dimensional DCT coefficients. So the property here is like this term, which is the first term in the top left corner, which it contains the DC term, okay, which contributes most to our input sequence, and the term in the right bottom corner contributes least. So as we can see here in this input sequence, there are much higher low frequency components represented by the, like as seen by the DCT coefficient 5, then the high frequency components, because we have 0 here. Okay, so now that we have the DCT coefficients, let's try to reconstruct our signal. So we'll run this. X reconstructed So let's run this. X reconstructed equal to inverse DCT2 of C, which is a 2D inverse DCT. So the X reconstructed should be equal to our original signal. It is supposed to be same. So we can see input matrix X is equal to reconstructed matrix using the DCT coefficients. So now we know that if we have the DCT coefficients, we can create the original signal. We can obtain the original input sequence from it. Okay. Now let's move to a more complicated example for this DCT 2D DCT, which in this case we'll take a image instead of a 2x2 matrix. So as seen here, we have taken the input image cameraman.tif, like the image provided by the MATLAB itself. You can like access it directly, and then we create, since the values in this image are like 0 to 255 if it's a grayscale image, so using this double, it normalizes these values in between 0 to 1. Now we have created a figure with the white background here. So figure, the color is white. Okay, I am show, okay, displaying the original signal, and we have put the title original image here. So let's check the original signal here. Okay, it should be here, right? We can see figure 1, it represents the original image. DCT coefficients of this image are saved as a C image, coefficients of image, which are obtained by the performing 2D DCT on image, which is I here. Okay, so then we display these DCT coefficients, okay, by doing this log 1 plus absolute of C comma image, in order to decrease the dynamic range so that the lower coefficients can be displayed as well. And then we write the I am show to display the DCT coefficients, okay, on this figure, original figure. Okay, and like we'll write the title log of magnitude of 2D DCT coefficients. Okay, so now we can see here we have obtained the 2D DCT coefficients of our image, which is cameraman.tif. So here we can see, if we zoom it in, so these coefficients, DCT coefficients, which are at the top left, these represent the low frequency components of the image. Since this image has more low frequency components than high frequency components, so the low frequency components are dominant here. You can see low frequency components are dominant, and the high frequency components are nearly 0. So we can infer from this, if we neglect some high frequency components, maybe we can reconstruct this image. So we can do the energy compaction, which is basically what we do in JPEG. We only take low frequency components which contribute more to image than the high frequency components. Okay, so let's try to understand this. Now let's try to reconstruct this image first with all the DCT coefficients. So we'll do I reconstructed equal to DCT, inverse DCT. Again, we do inverse DCT on the DCT coefficients. Okay, we'll create a figure with white background and I'm show reconstructed. We'll show the reconstructed image, and we have it in the title here. So image reconstructed using all DCT coefficients. Okay, let's run this. Okay, now as you can see, since we have taken every DCT coefficient into account, so the reconstructed image will be exactly same as the original image. As we can see, original image here and the reconstructed image here, they are exactly same, because every DCT component of this 256 cross 256 image has been taken into account. Now let's do some compression. Okay, let's see if we only take few DCT components, so what will the reconstructed image look like. So let's try to take 32 cross 32. Now let's do the reconstruction of this original image using a limited number of DCT coefficients. Okay, first we'll define the number of coefficients that we want to take and the total number of DCT coefficients that are available in the image. So the total number of DCT coefficients, like the size of the DCT coefficients, will be given by the m comma n, which will be stored in n comma n, and it's given by size of c underscore image. Okay, so this c underscore image gives us the size of our DCT coefficients m comma n, which is supposed to be 256 cross 256 in this case. So in our case, we are interested in 32 cross 32 DCT coefficients. So let's see how our reconstructed image will look like using these number of DCT coefficients. First, we'll create this C low equal to zeros m comma n. We'll take only first k1 DCT coefficients in x direction and k2 DCT coefficients in the y direction. Okay, like the first k1 rows and first k2 columns from the DCT image, and then we'll save it as C low underscore low 1 to k1 and 1 to k2. Okay, and then we'll save it, we'll do the inverse DCT transform of this C low. Okay, these coefficients, these number of coefficients which are 32 cross 32, and save it as I low, image with the low number of DCT coefficients. Okay, so now we'll try to see this reconstructed image I low, which is created with the 32 cross 32 DCT coefficients. As we can see here, the image is a bit blurred. So basically the low frequency components are here, visible here, but there are few high frequency components that have blurred. When we have like neglected those high frequency components, it has resulted in the blur in the image. So if we increase the number of DCT coefficients, let's say from 32 to 64, and here we'll check the DCT coefficients of 64 cross 64. Okay, now it should be a bit better. Okay, so as you can see, now we have taken the 64 cross 64 DCT coefficients, so the image is a bit better. If we further increase the number of DCT coefficients, let's say 128, okay, so now we are supposed to get even clear image. Okay, now as you can see, using the DCT coefficients 128 cross 128, we get a much better image than the 32 cross 32 DCT coefficients. So you got the notion. So it depends upon the number of coefficients, DCT coefficients, that we take into account while compressing an image. So in this lab, we have seen linear convolution, okay, and then circular convolution for 1D signal and for 2D signal, and then we have seen the DCT for 2 cross 2 matrix and DCT performed on an image. So in next lab, we'll see the DFT on 1D signal, DFT on 2D signal, and 2D DFT using the 1D DFT. Okay, so this concludes our lab 1. Thank you.